Hello, everybody. Thank you for joining us in this webinar. My name is Paulo Dias. I'm a geostatistician. I've been working in data mine for almost 8 years, mainly with resource evaluation. Today, I'm going to present the step-by-step to perform sequential Gaussian simulation using Studio RM. The main approach of this webinar is to show you the steps and processes you must consider for running a set of realization rather than focus on the theoretical aspects of simulation. By the end of this presentation, I will mention some applications and giving more attention to the tools that DataMine offers us for starting using simulation on our daily routines. Okay, so let's start then.
On this diagram, I have selected the steps we should follow if you are considering more than one domain and the kind of application you are going to apply. So basically the main steps are those ones. So we need to define the variable we are going to simulate. If it has some preferential sampling, we must considering the declustering rate, because this method is very sensitive to the initial distribution. So you need to be sure we have the better distribution or the representative distribution for our variable. The next step is to transform this original distribution into a Gaussian distribution. After that, calculating the Module and the variogram for the n-scores. Basically, this Module is to validate the hypothesis of multinormality between pairs of these samples. Then we get this the variogram model for this n-score. We can perform the simulation, and then we have to validate that simulations. And once we have validated that, we can start applying for whatever you want. Okay. So the data set I'm going to use is the well-known Walker-Lake data set. It's a 2D data set, as you can see here. And we are going to start taking a look on the histogram of the variable v that we are going to simulate. So I'm going to select the file here, this select the variable v, and I would like to see cumulative, that's it. Some statistics, predictions of variation, number of samples. So, what else? We can make some change here. And change to frequency. Then so that's the histogram for the variable v. right? That's the distribution. I'm gonna save this file. Cluster, since the cluster variable, I'm going to save as well the cumulative. Let me change that one. 100. Okay. Cumulative histogram CV variable. So as you can see, we have some preferential sampling here in that region. And so in this case, we need to consider the declustering rates. So for doing that, we need to calculate them. There is a process here called grid DC. So what we have to do is just getting the variable. I'm going to consider the, I have to put the name here for the output variable, output file, sorry, and weight, the clustering weight, select the coordinate of the samples and the variable as well. I'm going to retain the minimum grade, so the option 0. My grid will start with 10, and the maximum will be 100. And I will increase the size of the cell by 10 by 10 until reach this 100 meters here. The factor for Y and X, I'm going to consider the same rate for changing the size of the cell. And by Z, I would like to consider a rate of 0.1. And I will do this analysis at 10 different origins. And I will select this Excel file. They are going to plot for us the results. So if I click OK, it's gonna run. Oops, it's appearing here. Okay, good. So the minimum cell size here, let's check here. Okay, what I have, so I have the minimum mean value for that cell size, 318. Basically it's the average grade for this variable. So I have generated this file here, including the weights, right? So let's build again a histogram for that as well. Is the clustering variable V, the clustering weights. Okay, let's check. Let's see the change. You can already see how it changed. And 10. And the minimum maximum, mean, and efficiency of variation. So that's my new distribution. Okay, I will save this as well. So it's a histogram of P, but the cluster one. And I have the cumulative as, oh, sorry, I have the cumulative as well. Uh, 100. Okay, that's it. Yeah, the cluster. So as I said, it's this method is very sensitive to this distribution. So make sure you are doing whatever is possible to get the right distribution for that variable. Good. The next step is to transform this variable into a normal distribution. So there is a process here on estimate, transform to normal, the n-score process. Basically, it's quite simple. You just need to select this file containing the distribution and the samples and the weights, the clustering weights. I will put the name here. Maintain the same name, just adding here n-score. The grade will be V, and I'm going to use the clustering weights here. So just that. It's quite simple. Okay, let's have a look on that again. So now I have this variable n-score. Don't forget to apply the clustering weights. So let me change here, put it in the frequency. Minimum, maximum, total samples, mean, variance, variation. Right, then 4, 5. Oops, change this as well. Okay, so that's my distribution. So my original distribution now, I have transformed it to a very symmetrical distribution. I'm going to save as this chart again. Histogram and score clustered, and here I will see the cumulative as well. Good. And score. Good. So we are ready. We are ready to build our experimental variogram. So it's also quite simple. What you have to do is come here on estimate, and there is this option calculate. Name of the process is vgram, and you have just to select this file containing the samples and the normal score. Experimental variograms and select the coordinate of the sample files, and in score I will also do it for B. Okay, so we have some parameters here. You are not going to use all of them, only the basic ones, mainly the lag. I'm going to use 10 meters and a tolerance for this lag, a tolerance of 5 meters. I will run only 20 lags. The initial azimuth will be 0. The horizontal tolerance angle, I'm going to use 20. The increment, horizontal increment, will be 90 degrees, and I'm going to do on that plan 2 variograms. The dip as well, I don't have to consider because I'm working at 2D. So basically, if you want to calculate on that direction, you can just put here the same tolerance, put an increment if you want, but you're not going to generate, right? The seal hard is the corridor. Basically, you are going to select these samples. That's it. That's the only parameters you need to consider for this 2D variogram. Okay. The next step is just to click here OK for running it. It's quite fast. And for visualizing these experimental variograms, please come. We have to come here and click on Fit. There's a chart option for loading these experimental variograms. Okay, if I select here, I can see these experimental variograms for the N score. Good. I will ask to see the number of pairs. Actually, I'm going to consider only the points that have more than 50 pairs, right? I'm going to modeling this the variogram I will normalize this variogram just to be sure that the variance is going to be 1. The seal is going to be 1, right? Let me change here the formatting of the chart. Okay, that's it. And I'm gonna modeling using an isotropic structure, actually 3 structures. So they're going to open 2 individual windows, so I can start modeling that. It's quite good variogram to model. Okay, I have to lock this seal here for not changing anymore. That's it. That's good. Perfect. So for saving this model, just come here and variogram model. I'm gonna choose save it here 1 4 and score. Okay. Good. If you want, of course, you can save this model. Module. Oh, sorry. No. And now it's the imagine. Okay. Yes. Oh, sorry. It's possible if you want to display this the variogram parameters. I think it's a good idea to consider that on the same chart. So let's save it again here. Just okay, let's replace and that's it. So now I have my model and just for not losing this chart here, I'm going to open another window just for us to have a look on another important aspect, that is the Histogram.
We have now the option as an output of the GrA process, this Histogram, right? It's quite useful for helping us to define if our random function is a multivariate Gaussian. It's a complementary step in which we calculate the ratio between the variogram and the Histogram, and should be a constant equal to the square root of p, the number p, constant p. And of course, there is the indicator approach as well. We are not going to verify that hypothesis here, but just to let you know, it's important to consider that before running these simulations, right?
And now we are ready to run the simulation. The process we are going to use is you can find it here on Estimate, Sequential Gaussian Simulation. We need to consider first the initial samples. Don't need to use as input the normal score. This process here is going to transform the variable into a normal distribution for doing the simulation. So basically we need these normal scores only for calculating these experimental variograms. So the sample file, the variogram model. Let me update this. What is my variogram model? Let me check here. Let's see the sample file. Yeah, it's here. Sample file, the variogram model. And I have a prototype. Basically, it's the grid I'm going to simulate. As an output, I will have points, a file with points, and a model as well. And some statistics, if you want to take a look on that. Stat table. Okay, good. Here we have to select the coordinate of the samples, the variable, and then the clustering weight, because they are going to transform internally into a normal distribution. If you have to say the minimum grade and the maximum grade. we are going to transform that distribution into a normal distribution. The minimum and maximum allowed grade for the simulations. So I'm going to use the same on the sample file. Of course, it could be different. Sorry, 10. These 4 parameters here are related to this distribution, and basically on the back transforming of these simulated values. Basically, we have to define a function from for the lower tail and the upper tail of this cumulative distribution. Basically, we have for the lower tail 2 models, a linear interpolation and power model. I'm going to use a power model with a power of 2. For the upper tail, we have 3 options: linear interpolation, power model, and hyperbolic. I'm going to use this hyperbolic here with a power as well of 2. Then we need to define the number of simulations. I'm going to run 100 simulations. My grid, the grid I'm using here is, if I'm not wrong, 10 by 10. And on these 3 parameters here, we are going to control the discretization of this block. So you basically should define the number of points inside if cell. I'm not going to discretize here, just to do not lose time in running the process, but basically it's that. If you are not working with a prototype, so you have to define a prototype here, or the grid size. So we don't need to change any of these variables because we already have this initial prototype. And the seed, you can change that. Minimum number of original samples to use on the simulation, I'm going to leave 1. Maximum number of original samples, I'm going to use 32. 32 for the maximum number of previous simulated points as well. The next steps we should consider is the search volume. So in that case, I'm going to use the same. Let's check the value of our variogram. Let's take a look here. Have a look here. We have this 135 and 70 basically for Y and X. So in X 70, 140 basically. I'm gonna use 1. So that's there is no rotation. The kriging type, simple kriging, 0. Okay, and that's it. That's basically the parameters we should consider: minimum, maximum grade, type of transformation, minimum, maximum for the simulated values, the behavior of the shape of the distribution for back transforming, number of simulation, discretization, the seed, minimum number of original samples, maximum number of original samples, maximum number of previous simulated points to be used, search volume, rotation of the search volume, and kriging type. Basically are that. So the next step is to run the process. It's gonna take a couple of minutes. Okay. Okay, good. Now we have the simulated block model. So we have generated this model. Let's have a look on the output file. So I have 1, 2, 3, 4. Let's see, 100 simulations, right? On that initial grid. As I said, I said it was 10 by 10, but it actually is 5 by 5 by 1 grid, right? Okay, that's it. That's one of the output. So the block model with the same size of the prototype, because I didn't apply discretization. If I put a discretization of 2 by 2, so I will get a block model of 2.5 by 2.5. So it's how this discretization points works. And I have also a point file, so I'm gonna tell you later how we can use this point file as well. It's a very important file for us. Of course, these points have the same spacement of the initial grid size, 5 by 5, because I didn't use any discretization option. And there is another file we should have a look. Is the stat model. So what I have here, a comparison between the statistics for each simulated value or each realization. So for simulation 1, I have an average grade. For simulation 2, an average grade, and so on. So I have as well on the same file for the original samples and an average of all simulations that will be here on these all files here. So that will be my E-type basically. Okay. Close. So we have generated 3 files: a block model, a point file, and some statistics. Okay, so let's have a look what we did until now. We have selected this sample file, okay, defined the clustering weights, perfect, transformed it into a Gaussian distribution, okay, calculated the maddogram and the variogram, model this variogram, and perform the simulations. Now we are going to start considering the validation steps we have. Basically, we are going to see or check if if my simulations are reproducing the histogram of the samples, and if I calculate experimental variograms of these simulated points, if it's oscillating around my variogram model. So with that, I will try to verify if my simulations are reproducing my variogram and the distribution of the samples, right? Let's see how you can validate that. Okay. let's see here. So the first validation I'm going to consider is I will try to have a look how the average grade of these simulations are in relation to the average grade of the samples. So we are going to come here and build a new histogram. I will use this stat file, this one, and I will calculate the histogram for the mean of the simulations. So let's consider here this option here. I will see the total samples, maximum, mean variance, coefficients of variation, and here is 100, then let's see. Let's see here. 1000. See. Oh, sorry. 6 here. 40. Okay. Okay. Yeah. Okay. So if you remember, the cluster average of the samples was 318. So it's something close to here. It means, of course, we are considering on this histogram as well the type and the sample, but that's good to see that it's oscillate. My average, the cluster average of the samples are here inside this histogram in a point more or less here, right? So it's good. It's one chart we can use to validate. So his histogram mean similar. Another validation we can do is to see if I get this simulated point model, the simulated model. I'm going to select all the simulations. Check here. Okay, performance. I was asked to see only the cumulative, and that's it. Calculate. Oops, I forgot to put here compound chart. I have to change here for 0. Oops. Okay. That's the cumulative histogram for all simulations. If we check here, we can come back here. Let's see. What I have here is cumulative. Let me see. That's not the declustered one. That's, I think, is the declustered one. So we can we can compare more or less the shape of this distribution, but it's more or less close to each other. So which means we can easily see that it's oscillating around this. It's quite similar, the shape, right? That's one way we have for validating it. So the next step for validation is to check if the variograms of these simulated values are oscillating around the variogram model. So for doing that, we need to calculate again the experimental variograms, but now for the simulation. So if I put here model, I will put the same name here, experimental variograms. Now for these ergodic fluctuations, as we usually call this variogram chart. Oops, it's model, not varmod. Okay, I will select the coordinates, the new coordinates. I'm not going to do it for all simulations. I will select only 10 simulations here. Let's use one more, and let's set this 100. Okay, and the parameters I'm not going to change, will be the same. So just click here on run. It's gonna take a few minutes. Oh no, it's ready. That's good. Okay, and for visualize this, I'm gonna use the same. Oops, what is it? It's here. What is it? Okay, I'm gonna use the same chart used for modeling the initial variograms. Okay, so what I have here, let's consider one direction only. So this direction here, I'm gonna load this new experimental variogram. Okay, and I will try to have a look here. Load this for the first simulation. Good. For the second, third, fourth, fifth, and Okay, just to help to visualize, I'm not going to see this. Okay, just see here. Oh. Okay, that's it. It's quite good. It's a really important validation. We need to consider this validation. If it's not oscillating around the model, we should change the parameters or even the variogram and run it again. So I'm going to save this one as an example. Mod fluctuations. Okay, good. So basically, these are the steps we should perform for run a sequential Gaussian simulation using Studio RM. Prepare the samples, check for preferential sampling, normal score transformation, experimental variograms, madiogram for the multinormality assumption, run the simulations, and the validation, right? There is a really important process here, this CS model. Let me show you. If I get these point files, as I said previously, it's a really important file for us. For example, if you want to reblock these point files into higher blocks, we can use this process, right? Or even if I want to calculate the E-type on the same block model, I should run this process. So I will have a sim mod, a simulated model, as well as stat mod, some statistics. I'm going to calculate some statistics. I have to select the grade, B, and take a look, the same discretization. If I put here 1 by 1 by 1, I will get the same 5 by 5 by 1 block. If I put here 2 by 2, I will have a 10 by 10 block, right? So I will leave just 1 by 1 here, and I'm not going to change these other parameters. You can also consider cutoffs for calculating for each block the proportion above each of cutoff and the average grade and the proportion above this cutoff. So let's just run, and I will show you the type of output we get from this process. It basically, if you want to change this point support for block support. Okay, finished. Let me show you this sim mod. What's the difference? That in this model we have the E-type. As I didn't reblock, I have the same original block size. And on this stat mod, I have for each block, for example, the coefficients of variation for each block. So it's a very useful information. The median and some other parameters for the block distribution: minimum, maximum, mean, variance, standard deviation, standard error, skewness, kurtosis. Basically, it's that. Now we are going to have a look on some applications and what DataMine have for you to start applying it in your daily routine. Okay, let's have a look on the applications. You may ask me how we can apply simulation on our daily routines. The answer is quite simple, right? Because what you do with estimated model, you can also do using simulations. And the problem is that when you work with simulations, you have to manipulate a huge amount of data. So basically that's the difference. And you need tools for manipulating that data. But the idea is, I try to summarize this idea on this chart, is basically you have a single estimated model, you have an output, a true value for the output, you don't know that, and with your estimated value, you are going to get a result that could be close or not to the true value. Working with simulations, you are going to generate many possible realizations of scenarios of the deposit, applying the same function. And instead of getting just one single result, you can get, in this case, more than actually a distribution of results, right? So that's why you need a tool, an appropriate tool for help you generate these results. I select here two very common applications, one for mineral resource classification, when you can define confidence limits for help you define these categories of resource. And we also can use that for help optimize drilling spacing. These two applications are quite common. You can easily find cases where people are working with these applications. And I would like to show you two solutions that DataMine have for helping you using that. The first one is the GrA module on NPVS. Let me show here. Oops. Basically, it's quite simple. The process is quite the same. You need a block model with the estimated grade and also with the simulations. What we are going to do is to exactly the same, import the model, create an economic model, run the ultimate fit for the estimated value. Then we have some additional options. We have to import the simulations, actually just read the simulations. We are going to apply, we are going to apply this economic model on that simulations, right? And then we can run, evaluate these simulations against the optimal structural sequence we have generated, or we can also make these risk-rated bits. What is that? You can. The idea is, I'm going to optimize these 100 simulations. I'm going to generate 100 bits, and this 100% safe bit will be the bit which all blocks I'm mining in these 100 simulations. So if there is a block that is going to be mined for all these simulations, it's 100% safe block. So the group of these 100% safe blocks will for the 100% safe bit, and I can do it for for the other ones. For example, I have here, let's just show you this report. So I have the 100% safe, 90% safe, 8%, 7%, and so on. I can choose ultimate bit, not based anymore only on the economical parameters, but considering as well the geological uncertainty. There is some, basically is that a pitch with 100%, 50% safe, 10% safe. That's a section here just to show how it can oscillate.
I have here basically two approaches for selecting the ultimate bit in these first two charts here. I have basically a way I usually consider for define the ultimate bit. So I have a chart considering the strip ratio and the NPV, and the NPV and the total ore. When my NPV is not changing anymore, basically if I have a considerable amount of ore, and if my strip ratio is increasing as it is increasing, as you can see here, so basically in that point I define my ultimate bit. On these two charts here, what I have is the risk rated bits, so the 100% safe until the 10% safe. I'm comparing the NPV for, let's have a look on this 100% safe bit. The difference between the NPV is higher. The difference between the strip ratio is not too much. It's very close to each other. The 100% safe bit and this ultimate bit I have selected here. The same occurs for the total ore. The NPV is lower, and the total ore is quite the same of this here. Basically, what the difference that I'm losing on my NPV using that approach, but I'm not neglecting the grade uncertainty, right? So here we have a table comparing these two approaches for define the ultimate bit. So the NPV for the traditional approach is 98 against this 72 for the 100% safe bit. But the amount of ore is a little bit higher, and the strip ratio is a little bit higher. In terms of ore, they are quite close apart this NPV, but we need to consider and take in account that we are assuming and considering on that approach the geological uncertainty.
So let's have a look on the second example. It's related to MSO. Basically, it's a process for optimizing stopes. So where we have to define a block model with the grade. You can use for optimize the slopes the E-type of the simulations or the estimated graded, you decide. The wireframe to control all the geometrical parameters and economical parameters as well. And here we have an option to consider some sensitivities based on that simulations. In that case, I'm considering only 10 simulations just to run it fast. So it's quite simple. The only additional step is to import a model with the simulations, select the simulations you want to use, define a percentage target for this probability. I'm going to talk you what does it means right now. And actually, on the next slide. And in to run, it's exactly the same. It's not going to change. But let me show you the result. As after optimizing these stopes, what I'm going to do is to calculate the average grade of the blocks inside this stope for each simulation. So I'm going to get distribution of grades inside this stope, like that one. So I will have a minimum, maximum grade, an average grade. I can find somewhere here the estimated grade, the average of the blocks inside, right? And so that's the cutoff I have used to define this stope. So in that case, applying this cutoff on that distribution, there is a probability of 88% of the average grade of this stope being higher than the cutoff, right? That's the idea. And you can select only the stopes above a certain target or confidence limit. For example, these ones are the stopes that have a probability of being above the cutoff higher than 20%, and here higher than 50%, and here higher than 80%, right? That's the idea of this. You can use that for classifying resource, just to be more start considering economical parameters for classifying resource in that case. So there is many possibilities. Datamine have introduced these two new tools for helping and encourage you to start using simulation on your daily routines. We also are able to provide some trainings, consultant services, guidance, and to help and encourage you start using simulation. It's can really aggregate some interesting results and analysis on your projects. So thank you very much for joining us. I think we have a couple of questions. We still have time to answer this question. Let me take a look on that.